Welcome to this explainer. Today, we're tackling one of the absolute most mind-bending concepts in all of physics, time dilation. We're going to dive right into Einstein's theory of relativity, and don't worry, we're skipping the dense, confusing math. Instead, we'll just build a really intuitive, step-by-step understanding of how our universe actually works.
So let's just jump in with a super basic question. Does time pass at the exact same rate for everyone? I mean, everyday experience screams yes, right? We basically walk around assuming time is this fixed, absolute ticking clock in the background of the universe. A second for you is a second for me. Well, prepare to have that assumption totally shattered.
To really grasp just how weird reality is, check out this staggering fact. The legendary physicist Richard Feynman actually calculated that the center of the Earth is roughly 2.5 years younger than the Earth's crust. Think about that. The planet formed all at once, so how on earth could the inside be younger than the outside? It instantly sets the cosmic stakes here. Time is definitely not absolute. It bends, it stretches, and it behaves completely differently depending on where you are and how fast you're moving.
Let's look at the illusion of absolute time.
To understand why the Earth's core is literally younger than its crust, we have to start with Albert Einstein's game-changing realization. It's the core postulate of special relativity. The speed of light is constant for all observers, period. No matter how fast you go, light always zooms past you at roughly 300,000 kilometers per second. Even if you tried to chase a light beam in a high-speed rocket, it doesn't appear to slow down relative to you. It still pulls away at that exact same speed. Because that speed limit is fundamentally locked, well, something else has to give. Space and time themselves literally have to warp and stretch just to keep that speed constant.
And that leads us to the formal definition of time dilation. It's the difference in elapsed time as measured by two clocks caused by either a relative velocity or a difference in gravitational potential. Simply put, a moving clock actually runs more slowly than a clock at rest from the perspective of an outside observer. And to be perfectly clear, this isn't some mechanical glitch with the clock itself, it is the actual fabric of time slowing down.
Which brings us to motion and the light clock.
To really visualize this, let's play cosmic detective with a classic thought experiment. Imagine a hypothetical device, a light clock, floating inside a space station. It's basically just a single photon of light bouncing straight up and down between two parallel mirrors. Every time that photon hits the bottom mirror, the clock ticks. It's the ultimate perfectly precise metronome. Now, if you're standing right next to it, you just see that light bouncing in a simple, straight vertical line. But here's where Einstein's brilliance really shines. Imagine that exact same light clock is on a spaceship flying incredibly fast right past you. As the ship moves horizontally, the photon inside is still bouncing up and down. But because the mirrors are moving forward while the light is traveling, from your stationary perspective outside, you see that bouncing photon trace a much longer, diagonal, zigzag path. But remember our golden rule, the speed of light absolutely cannot change. So if the light has to cover a longer physical distance along that diagonal path at the exact same speed, then each tick of that clock literally has to take more time. The moving clock ticks slower.
Now, physicists calculate this time-stretching effect using something called the Lorentz factor, represented by the Greek letter gamma. At everyday speeds, like driving your car or flying in a jet, this factor is so incredibly close to 1 that we don't notice any time dilation at all. But as an object's speed creeps closer and closer to the speed of light, the denominator in this equation approaches 0, and the Lorentz factor skyrockets toward infinity. Suddenly, those time-stretching effects become absolutely massive.
This leads perfectly into the famous twin paradox.
To see how these abstract equations apply to human aging, let's walk through this classic scenario. Imagine you have a pair of identical twins. One stays right here on Earth, while the other blasts off in a rocket at relativistic speeds, meaning a significant fraction of the speed of light. Because the traveling twin is moving so incredibly fast, their time dilates. It slows down relative to Earth. When that rocket turns around and comes back, the traveling twin steps out of the ship and is genuinely, literally, younger than their sibling. Now, it's called a paradox because, hey, motion is relative, right? Couldn't the astronaut just say the Earth was the thing moving away from them? But it's actually not a paradox at all. The situation isn't perfectly symmetrical. The traveling twin changes their inertial frame when they fire their engines to turn around. That acceleration proves they are the one moving, so they're the one who genuinely ages less.
To give you a sense of the sheer scale we're talking about, imagine an astronaut travels to our nearest star system, Proxima Centauri, going 90% the speed of light. People back on Earth will wait 4.71 years for them to get there, but for the astronaut, because of that extreme speed, their clock runs way slower. The journey only feels like 2.06 years to them. They basically just jumped over 2.5 years right into Earth's future.
Now, let's talk about gravity's pull on time. We need to shift gears from motion to gravity, because speed isn't the only thing that warps time. We also have gravitational time dilation. Simply put, the stronger the gravity you experience, the slower time moves for you compared to someone in weaker gravity. Clocks located deeper down in a gravitational well, like, say, closer to the surface of a really massive planet, run more slowly than clocks floating way out in deep space. And unlike the relative velocity we just talked about, gravitational time dilation isn't reciprocal. Everyone in the universe agrees that the clock closer to the heavy mass is the one ticking slower, which, circling back, is exactly why the center of the Earth is younger than the crust. It's deeper in Earth's gravitational well.
And this isn't just sci-fi. It happens to real people all the time. Take a look at this number, 20 milliseconds. Cosmonauts Sergei Krikalev and Sergei Avdiev spent massive amounts of time aboard the Mir space station and the ISS. Because they were constantly moving at super high orbital speeds, their time slowed down. They quite literally time-traveled into the future, experiencing about 20 fewer milliseconds than the rest of us down here on Earth.
If you want rigorous, hard scientific proof, look no further than the brilliant Hayflick-Kading experiment from 1971. Scientists synchronized these ultra-precise atomic clocks and just flew them on standard commercial airliners around the world, going both east and west. They had to crunch the numbers to account for both the speed of the planes and their altitude away from Earth's gravity. When those planes landed, they compared the flying clocks to reference clocks left on the ground. The results were absolutely flawless. The flying clocks lost and gained nanoseconds exactly as Einstein's relativity predicted.
Which brings us to time dilation in everyday life. At this point, you might be thinking, okay, sure, this is super cool for astronauts and atomic clocks, but why does this actually matter to me? Well, let's connect these cosmic concepts right to your daily routine. The Global Positioning System, GPS, relies on a huge network of satellites orbiting the Earth. And these satellites are stuck in a massive relativistic tug-of-war. On one hand, they're moving at incredibly high speeds, which, according to special relativity, slows their clocks down by about 7 microseconds a day. But on the other hand, they're also flying 20,000 kilometers above the Earth, meaning they experience much weaker gravity. And according to general relativity, that weaker gravity speeds their clocks up by about 45 microseconds a day.
So here's the absolute crucial point. If engineers didn't actively correct for that net difference of 38 microseconds every single day, the whole GPS system would accumulate massive errors. Literally within minutes, the location pin on your smartphone would drift by miles. Without actively accounting for Einstein's theories of time dilation, modern navigation would completely fail. Every time you map a route to a new coffee shop, you're relying on the fact that time is flexible.
So let's bring it all together and summarize the core takeaway of this explainer. Time is not an absolute parameter. It is actively influenced by factors like your speed and the gravitational fields around you. Our entire understanding of reality is fundamentally woven into a single dynamic fabric called spacetime. The faster you move through space, the slower you move through time. It's as simple and as mind-blowing as that.
Which really just leaves us with this profound, lingering question. If the passage of time, like the very rhythm of our lives, bends to the will of motion and gravity, what else about our reality is just an illusion? I really hope this journey through time dilation sparked your curiosity to keep exploring the incredible mysteries of physics. Thanks for joining me on this explainer, and keep questioning the universe.